Okay, welcome to Chapter 2, where we're going to actually divide Chapter 2's content up into two sort of big chunks. One is significant figures, which is this Tegrity recording, and then there's going to be a second Tegrity recording, which will focus in on unit conversions and dimensional analysis. So this one is Chapter 2A, and the other one will be Chapter 2B. You want to make sure that eventually you listen to both of them. So significant figures. The question we're going to start off with here is one that you might have thought about, which is when you go to the gas pump and you're putting the gas into your car, how do you know that you're actually getting the amount of gas that the meter says you're going to get? Well, it turns out that somebody does something to that meter. They measure it. Now, they could come by, and if we're just sort of hypothetically considering how this might happen, they might come by with their container and they'd pump some gas into it and measure how much actually came out into the container and then compare it to the meter. So in terms of you as a consumer, we might be interested in asking, would it make more sense from our point of view to have a container like the one outlined here in A, which is marked to the 100-gallon marks? And those are the only marks that are made on it for measurement. Or another container, a second one, same size, which is container B. And in container B, you actually have markings to the 10-gallon mark. So the question for you to sort of stop and consider here is, which would you prefer to have this person who's coming to measure what's coming out of the gas tank in the ground to check the meter with? Would you prefer they check with A, or would you prefer they check with B? Well, this is actually a significant figure question. When we record measurements, we record all the numbers that we're certain of and one that we guess. And that collection of numbers, everything that you know for sure and the one where you guess, is called the significant figures for the measurement. And because you're guessing every time you make a measurement, all measurements have some degree of uncertainty in them. And you're right, that uncertainty is located in that very last number, the place where you guessed. So if I have container A, which is marked to the 100-gallon mark, as we drew earlier, and I'll redraw here so we can talk about it. Here's 100, here's 200. And let's say that they've measured and put some liquid into the container. Down here, here's my liquid. And we want to record, given this container, what the measurement would be. So take a moment, think about what you would write down for that. Okay, now that you have one in your head, or maybe written on a piece of paper close by. When we look at this, what are we certain of? Well, we're certain that it's not over 100 and that it is over 0. So we're certain that it's this certain size where it's somewhere between 0 and 99. So that means I should have at least two numbers that I'm filling in. Now, the first one that I'm going to fill in, because I know it could be 90 or 80 or 70 something, when I look at that, I'm pretty much guessing, right? So when we read to liquids, what we're doing is we're reading to what's called the bottom of the meniscus. So my pen may not show this super well, but I'm reading to the bottom of the layer of the liquid. So that's where I want to estimate to. And when I do that, it looks to me like it's a little farther up than half. So I'm going to say it's 60 something. So I'm going to put a 6 in the 10th spot. Now, did I guess that number? Indeed, I did, right? I guessed this. So the next number, if we go back and think about what we just said with measurements, we record everything that we're certain of and one guess. So if I'm guessing in the 6th, in this position here, in the 10th point, then what should I put in for the ones? Well, I don't want to guess again, because if I guess again, then I'm implying that there's a greater level of certainty in the measurement than there actually is. But since I've already guessed once, then now I just have to fill in a digit to hold place for me, which is a 0. So I end up with a measurement of 60 gallons. Notice I've got my unit there so that we know what volume we're talking about. So if we were using container A, we would say I've guessed in the 10 spot and I've used a placeholder in the 1 spot. So the uncertainty in this measurement would be plus or minus, where did I guess? Well, I guessed in the 10 spot. So that means my uncertainty is plus or minus 10 gallons. If instead we're looking at container B to do our measurement, remember container B was marked to the 10-gallon mark. Just draw this in here. Here's my 100. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And again, we'll put in our meniscus for our hypothetical amount of liquid. Here's my liquid. And again, I'm going to look to the bottom of the meniscus to read, whoops, and I'm nowhere near the bottom of the meniscus there. Let me erase that. See what I can do. I think I want to erase like that. Whoa, except I'm going to erase that too. Hold on. You can see I'm new to this. Smart technology. All right, there's my liquid again. There's my container all fixed. Here's my bottom of my meniscus. And so when we look here where the bottom of the meniscus comes in, it looks like it is going to be greater than this one here, but less than that one there. So counting up, 1, 2, 3, 4, 5, 6, 7. So it's definitely greater than 70, but definitely less than 80. So when I go to record my measurement, I am certain that it is 7 something. So I'm certain here in the 10th place. In the 1's place, now, since I'm certain, I haven't guessed yet, and I want to make sure that I guess once, I am going to estimate, looking at where my meniscus level comes in there, and I'm going to say it's pretty close to the 7. So I might say that that's 71 gallons. And notice here, I'm going to stop guessing at that point. I'm not going to add any more digits. So my measurement is 71 gallons. And my uncertainty in my measurement in this scenario is plus or minus, what do you think? It's plus or minus 1 because I guessed in the 1's place. That's where my uncertainty is located. I was certain in the 10's place. So my uncertainty directly correlates to where I guessed, hence that plus or minus 1. So back to this question of how we determine significant figures. All non-zero numbers are going to count as significant figures. Zeros are going to count sometimes and sometimes not. So sandwich zeros are always going to count as significant figures. Leading zeros will never count, and trailing zeros will count if there's a decimal point explicitly stated in the number. So let's talk more about what a sandwich zero is and what a leading zero is and what a trailing zero is. So sandwich zeros, these are zeros within a number. For example, if I have 504, that zero that's highlighted in red, that's a sandwich zero. It's a zero contained within the number. 2002 has 2 zeros in red because I've got 2 zeros sandwiched within the number. 0.01089 has 1. Those 2 front zeros, these guys out here, these are something else. They are not within the number. So then we might ask, how many significant figures are there in 2002? Well, if we back up for a second, we said that all non-zero numbers count as significant figures. Okay, and we said that sandwich zeros always count as significant figures. So in 2002, the 2 is significant and the 2 is significant because they are not 0. And both of these zeros count because they are sandwiched. So my total number of significant figures equals 4. And I will tend to abbreviate significant figures as sig figs. 4 sig figs in 2002. Oh, and there's the answer, written much more clearly. Leading zeros are zeros that come at the very front of the number, notice down here in red, those zeros come at the front of the number. They are leading zeros. They are placeholders, meaning that they aren't ever going to count as significant. And one reason we know this is that if I took this number and wrote it in scientific notation, I would move my decimal point 3 places and write it as 1.04 times 10 to the negative third, right? So what happened to those zeros at the beginning? Well, they're gone because they weren't significant. They were placeholders. Trailing zeros count as significant figures if there's a decimal point explicitly shown. So this is different than you might find in your math class where you put decimal points in willy-nilly wherever, kind of made things look nice. In chemistry, decimal points are going to tell you help tell you how many significant figures you have. So we are very careful about whether we have decimal points or not. So for example, we've got 504.0 versus 5040. In this case, 504.0, I have a trailing zero. And in 5040, I have a trailing zero. So those red zeros at the end of the number. But in 504.0, I also have a decimal point explicitly stated. In 5040, no decimal point out there. So that tells me, that when I look at the number of significant figures in 504.0, the 5, this 0 because it's sandwiched, the 4, and that end 0 all count as significant. So 504.0 would have 4 sig figs. 5040, the 5 counts. This 0 counts because it's sandwiched between two non-zero numbers. And the 4 counts, but the 0 at the end of the number does not count. So this one only has 3. So how many significant figures are in each of the following measurements? And here is where, this is one of those exercises where you're going to want to stop the integrity recording, just put pause right now, or not right now, let me finish talking. Push pause and actually run through doing these so that you can do a little self-test and see if you actually understand how to do significant figures. And if you do, fantastic. And if you don't, you might want to go back and watch the recording again or open your textbook and read the section on significant figures and maybe walk through some of the additional examples that are done in your textbook. So go ahead and hit pause. Okay, so we're back. When we look at 10,570, we're looking for which digits are significant. And we know that all the digits that are not zeros are significant. So the 1, and the 5, and the 7 are all significant. And then the question is, are all of those zeros significant? So let's consider the 2 middle zeros here and here first. Notice that they are sandwiched in between the 1 and the 5, which means that they're sandwich zeros. And sandwich zeros, if you recall, always count. This 0 down here at the end of the number after the 7, there's no decimal point. See? No decimal point there. So that tells us that the number of significant figures in this is actually here, 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 and not that last 0. So that would be 5 sig figs. 1.001 is 4 sig figs. I've got a 1, 2 sandwich zeros, and another 1, which gives me 4 sig figs. 0.09080, I have a decimal point explicitly stated right there. So that tells me that this 0 at the end of the number definitely counts as significant. What else counts as significant? Well, this 9, which is not a 0, and the 8, which is not a 0, and this 0 because it's sandwiched in between the 9 and the 8. What doesn't count are these zeros out here at the front. So this, let me use a different color here. This 0 here and this 0 here are considered to be leading zeros. Great, now they look like they're bleeding. They're considered to be leading zeros, and so they don't count as significant figures. So I just have 1, 2, 3, 4 sig figs. In 3.450 times 10 to the 6th, I've got a significant figure here with the 3, one with the 4, one with the 5, And because I had a decimal point explicitly stated, this trailing 0 counts as well. What about this stuff out here? Does that count as significant? Well, no, it doesn't. That's just telling you how many placeholders you have. So for significant figures in scientific notation, I'm only looking at the number out front. And that has 4 sig figs. In 7.0800 times 10 to the negative 4th, again, just looking at this number out here, I see the 7 for sure, the 8. I've got a decimal point, which tells me that these trailing zeros will count, and this 0 here in the middle between the 7 and the 8 will count as well because it's a sandwich 0. So that gives me a grand total of 1, 2, 3, 4, 5. 5 sig figs. We might also be forced to look at or I shouldn't say you're forced to. You might be asked to answer what's the uncertainty of each of these measurements. And keep in mind, where is the uncertainty found in a measurement? It's found in the last significant digit, where we guessed. So that means when we look at these numbers, now we need to figure out who's the last significant digit and translate that information into an uncertainty. So when we look at 10,570, we said that the last significant digit, we just walked through this in the previous slide, is the 7, which tells us that the uncertainty is located in the 10 spot. So when I'm asked what is the uncertainty of 10,570, the uncertainty is plus or minus 10. 1.001, my last significant figure, is also, in this case, my last digit. So the uncertainty is located in the last digit, and I see that it's 1, 2, 3 spots out from the decimal point, so it's 0.001 for my uncertainty. For the next one, my last significant digit is also the last digit, because that's a trailing 0 and there was a decimal point there, remember? So the uncertainty is plus or minus point, and I got to count my decimal places, 1, 2, 3, 4, 5. So 1, 2, 3, 4, pop a 1 in that last spot. 3.450 times 10 to the 6th, my last significant digit was here, and rather than writing out the number completely, although you certainly can do that, what I'm going to do is say it's plus or minus 0.001 times 10 to the 6th. So I'm just going to bring over my scientific notation placeholders. Same deal on the last one. Last significant digit is the last 0, so I have plus or minus for my uncertainty, plus or minus 0.0001 times 10 to the negative 4th. Okay. When we do calculations with significant figures, there's a couple of rules you want to remember. And one set of rules goes for multiplication and division, and one set of rules goes for addition and subtraction. So we're going to start with multiplication and division first. And the rule here is that the number of significant figures in the answer should reflect the smallest number of significant figures in the measurements that you used. So for example, if you had 5.0 inches times 3.90 inches, the question we're really asking is, how many significant figures should be in my answer? And to answer that, it tells us that we need to go back and decide how many sig figs were in this measurement and how many sig figs were in this measurement. And whichever has the least amount should be showing up in my answer as well. So 5.0, if we look at that, it's got a 5, which definitely counts as significant. It's got a decimal point and a trailing 0, which we know trailing zeros count when there's an explicit decimal point. So this has 2 sig figs. 3.90, for similar reasons, has 3 sig figs. So that means my answer should have 2 sig figs. So if you whip out your calculator here and put in 5 times 3.90, whoops, I put in the wrong thing. 5.0 times 3.9. I get 19.5 on my calculator. But the issue is, I need to report this as only 2 sig figs, which means I'm going to have to round, because right now 19.5 has 3 sig figs. But if I want to go to 2 sig figs, then I need to have a number here and a number here. And if I look past the 9, there's a 5 there, which means when I have 5 or greater past the number that I need to drop, then I'm going to round up. Well, what happens here is, if I round the 9 up, it becomes a 0, and the 1 changes to a 2. And so I end up with this. How many sig figs are in that number? Well, there's a 2, which is not a 0, so we know that counts. And there's a 0, but there's no decimal point right now, which would mean that this answer, as I have it written, would only be one significant figure. Ooh, what I want is 2. So the question is, how do I take 20 and turn it into 2 sig figs? Well, here's what you do. You write your 20, and you pop a decimal point on. So that's one way to do it. The other way to do it, some of you may have thought of, is to write it in scientific notation, 2.0 times 10 to the first. Don't forget your inches, or don't forget your units here. I had inches times inches, which is essentially inches squared. So either of those answers would be perfectly acceptable. In addition and subtraction, the answer is going to reflect the measurement with the largest uncertainty. So it's different than multiplication and division, and you cannot take the rules for multiplication and division and apply them to addition and subtraction and think that they'll work every time, because they won't. So in terms of this, we want to evaluate who has the largest uncertainty. So when I look at 5,400 down here, I see that the uncertainty is in the last significant digit. And if we look at this, I have a significant digit here, and here, and here. But my last 2 zeros don't count as significant because there's no decimal point explicitly stated. So that means that my uncertainty in 5,400 is going to be plus or minus 100, because uncertainty is going to be found in my last significant digit. On the other hand, when I go down here to 35,567, I've got a significant digit here, and here, and here, and there, and there, which makes my uncertainty a heck of a lot smaller. Now my last significant digit is in the 1 spot, so my uncertainty is plus or minus 1. Well, then the question is, how do we write our answer? If I just put it into my calculator, which I'm going to do right now, 50,400 plus 35,567 will give, my calculator will tell, whoops, I screwed it ahead. My calculator will tell me that the answer should be 85967. Well, that's good as far as my calculator is concerned. It's not so great in terms of chemistry class, because we need to evaluate significant figures and uncertainty. When I go back and look at my 2 choices here for uncertainty values, we see that my choices are plus or minus 100 or plus or minus 1. If I go back to the definition, the answer should reflect the measurement with the largest uncertainty. So, who has the largest uncertainty? The uncertainty of plus or minus 100. So that means down here in my answer, I need to write this so that it has an uncertainty of plus or minus 100. So what that tells me is that I need to go to the 100 spot, and everything after it needs to be placeholders. My last significant digit needs to be in the 100 spot. So that means this is significant, and the 9 is significant, but the 6 and the 7 are going to be replaced. Now notice, again, here we're going to run into some rounding issues, because the digit just past the 9 is greater than 5. So I'll write in 860. All of those digits are supposed to be significant, and then these last 2 zeros are supposed to be placeholders. Well, clearly I can't write the number this way and reflect the right number of significant digits or the right uncertainty. This is a number that, in order to show the correct number of sig figs, I have to write in scientific notation, because this 0 right here is significant, and as it's written, it doesn't show that. So putting this in scientific notation is going to be 8.60 times 10, and then I'm going to count 1, 2, 3, 4 spots. So 10 to the 4th. And that would be my answer. There are more examples in your textbook, so let's go ahead and look at 42A in your textbook. Grab my textbook here. So we're in Chapter 2, so we want to go to the back of Chapter 2, to the problems. which you can find starting on page 46. And 42a is on page 48. And it says, carry out the following additions and subtractions, expressing your answer to the correct number of significant figures. Assume that all numbers are measured numbers. So in 42a, we have 237. I'm going to write this over here. 237 plus 37.0. And I'm going to be careful to line up my decimal places here. Plus 7.0. So I need to add all of these together. And when I do that just using my calculator, I have 237 plus 37 plus 7. Let me check that. I think I put something in wrong. 237 plus 37 plus 7 gives me 281. So my calculator says this should be my answer. But we know we're in chemistry class and we need to think a little more deeply about this in terms of significant figures. The rule, remember, for addition and subtraction is the measurement with the largest uncertainty should be reflected in my answer. So I need to look at each of these and decide their uncertainties. When I look at 237, I have sig fig, sig fig, sig fig. Where is my last sig fig? Well, it's in the 7 is the last sig fig, so my uncertainty there is plus or minus 1. In 37.0, I have sig fig, sig fig, sig fig. My uncertainty is in the last digit. It's plus or minus 0.1. 7.0, sig fig, plus or minus 0.1 as well. So that means when I go back and look at these, the largest uncertainty is sitting right here, plus or minus 1. So then I look at my answer. Does that have an uncertainty of plus or minus 1? Yeah, it does. So that means that I've actually inadvertently written the answer correctly, 281. Now notice, if I had applied the rules for multiplication and division to this problem, I'd be totally messed up, because I would have thought that 7.0 only has 2 sig figs, and so my answer should only have 2 sig figs. But that's where the rules really set things apart. In addition and subtraction, it will not be necessarily all the time that your lowest number of sig figs gives you the correct answer, as we can see in this problem right here. Let's go ahead and look at 50F as well. In this case, we are doing multiplication and division, and it's a fairly complex, in terms of what I'm going to have to write on your screen. It's not a difficult thing to do, but. So F, I have 3.2 times 10 to the second, and that's multiplied by 3.31 times 10 to the sixth, divided by 4.00 times 10 to the negative second, negative third, that's a 3. And that's multiplied by 2.0 times 10 to the sixth. Okay, so first I'm going to put it into my calculator to see what mathematically it comes out as. So 3.2 times 10 to the second, that's multiplied by 3.31 times 10 to the sixth. Whole thing is divided by 4.00 times 10 to the negative third, and also divided by 2.0 times 10 to the sixth. And so when I get done just doing the straight up math on my calculator, I get 1,249,5,6,604, which is nice, but that's a lot of significant figures. When I go back and think about the rules for significant figures, we know that for multiplication and division, the smallest number of sig figs in my measurement should be reflected in my answer. So let's check sig figs. Here, I have 2 sig figs. Here, I have 3 sig figs. Here, I have 3 sig figs as well, and here I have 2. So the smallest number of sig figs in my measurement is 2, which means that over here on my answer, I only need 2 sig figs. So starting at the beginning of the number. Here's a sig fig, here's a sig fig. Everybody else has to become placeholders. So my correct answer is 1, 2, 0, 0, 0, 0, 0, 0, 0, 0. That's the answer. You could also write it in scientific notation if you wanted to. This particular problem, I don't have to write in scientific notation because I only needed 2 sig figs. And they're shown with my 1 and my 2. Homework problems. So we're done with our discussion of significant figures. Your homework problems out of Chapter 2 for this section would be 1 through 52. And again, I would encourage you to do at least the odds, if not more than that. Because the important thing to remember here is that when you're getting ready to take a quiz or do the online homework or one of our exams, how you know that you're actually ready for that assessment is if you can do any of the problems in the homework, in the textbook, without access to outside resources. So you want to make sure that you really understand these concepts. And you can only do that by actually practicing them, among other things. This group of problems actually includes some problems on the metric system and scientific notation. And these items are generally not new to students, so I don't tend to spend class time covering them because not everybody needs to review scientific notation in the metric system. However, if you don't feel super comfortable with the metric system and scientific notation, please make sure to do the homework problems that are relevant to those sections so that you can catch up. All right, we are done with that part. And now I need to stop recording.